This is the third in a series of videos about phase transitions. In the last two videos, we talked about vaporization and a specific type of vaporization called boiling, when the vapor pressure is equal to the atmospheric pressure. And so we focused hard on liquids and solids, and now we need to talk about transitions between other phases. We need to include solids into our mix. So let's bring back our three phases of matter. We have solid, we have liquid, and we have gas. So we've already talked about two of the phase transitions in fairly great detail. We talked about vaporization, which is the transition from liquid to gas, with the symbol delta H vape. And we talked about gas to liquid condensation. Call that delta H con. Okay, and so now there's some other phase transitions. We need to include solid in the mix. So when we go from solid to liquid, most of us call that melting, but its official chemistry name is fusion. Delta H fuse. And when we go backwards from liquid to solid, we call that freezing. And sometimes, even though it looks like we usually go up by one phase at a time, sometimes we can skip all the way from a solid to a gas, or we can skip all the way from a gas to a solid. We don't see it with water or with most of the things we use on an everyday basis, but there are compounds and there are situations when this can happen. So if we skip all the way from a solid to a gas, this is called sublimation. This is something that carbon dioxide does, dry ice. Sublimes straight from a solid to a gas. And if we were to cool the compound from a gas straight to a solid, this is called deposition. It deposits on a surface as it cools. We use the symbol delta H dep. These are the official phase transitions in their names, and you'll notice there's a delta H and enthalpy value for each of the phase transitions. And so let's think about how the size of the different phase transitions would probably compare to each other. So the enthalpy represents the amount of energy that a particular phase change takes. So let's think about increasing the temperature and starting from a solid to go to a liquid or a gas. So if our energy of a solid is down here, the amount of energy that a liquid has is a little bit higher, right? Liquid particles are moving a little bit faster. They're not as rigid. They're moving past each other. And so we need to put in energy to release the solid particles from their rigid structure and get them to move around. If we want to label that, that's our delta H of fusion, going from low to high. If we wanted to go from liquid to gas and draw in vaporization, we have to think about would it take the same amount of energy, less energy, or more energy than fusion. So going from solid to liquid, you're going from moving just barely to moving a little bit and moving around. And when we go from liquid to gas, we're going from moving around a little bit in solution to moving around a lot. Moving, taking the full shape of the container, this is a bigger transition. We have more of a push of kinetic energy that we're adding. So the gap is going to be larger here. The amount of enthalpy change that's needed to go from a liquid to a gas is larger in general than the amount needed to go from a solid to a liquid. And if we think about subliming, it's almost like taking both of those two smaller steps in one very large step. So this is not completely accurate, but roughly the amount of energy required for subliming is roughly the same as the amount it takes for fusion and vaporization. So it takes the most energy to sublime, the next most energy to vaporize, and the smallest amount of energy to fuse from a solid into a liquid. And so the values for water, to give you an indication of what these look like, the delta H of fusion for water is 6.02 kilojoules per mole. And the delta H of vaporization for water is 40.7 kilojoules per mole. So in this case, it takes 5 times as much energy input to go from a liquid to a gas as it does to go from a solid to a liquid. So this is a much larger number in general. So these enthalpy values are useful for telling us how much energy is needed to change the state. And so it's important to realize that while this phase change is happening, the temperature is not changing. The temperature remains constant during a phase change. So we can think about what the heat is going to. If we're heating up a substance, if we're heating up a glass of water, what is that heat doing? When we put that energy into the system, it's increasing the thermal energy, the kinetic energy, the speed of the molecules is moving quicker and quicker until it cannot move any quicker as a liquid. And when it reaches that boiling point, that transition temperature, instead of the energy going into changing the kinetic energy, it is funneled into changing the phase, breaking those intermolecular forces that hold liquid molecules close together and breaking them to allow it to turn into a gas. So even if we put in a constant amount of energy, the temperature stops changing until that phase change is complete. So that energy that's put into the system is used to break intermolecular attractions. Instead of increasing the kinetic energy like it does when there's not a phase change happening. And the easiest way to picture this is with a plot. So we're going to plot how much heat we're adding to the system here. And we'll plot temperature on this side. So as we move to the right in the graph, we're adding more and more temperature. So let's say we're starting with a piece of ice, and a piece of ice is going to be a solid. So here's our piece of ice at a particularly low temperature. What happens as we add heat to the system? Well, as long as it's below its freezing point, as we add heat, the temperature of the ice increases. So this is ice. And it increases until we reach the transition temperature, which is the melting point or the freezing point, whichever you prefer. And then once we have enough heat to reach that melting point, even though we're continuing to add heat to the system, the temperature is not going to change. The heat is going to go into the transition from a solid to a liquid. So here, at this part of the graph, we're going to have ice and we're going to have water while that transition is happening. So once we finish changing all of the ice into water and we only have liquid, if we continue heating, now the heat is going to go to increasing the kinetic energy and increasing the temperature of that water. And we'll keep going, heating the water until we get to the next transition temperature. And the transition temperature between liquid water and gas water is the boiling point. And once we reach that temperature, which is 100 degrees at normal pressure for water, all the heat that's added goes into breaking those intermolecular forces and converting that liquid into a gas. So here we have water and steam in the transition between the two. And we continue adding heat until all of the liquid has turned into a gas. It remains at 100 degrees Celsius until that process is finished. And once the process is finished, if you continue to add heat, It'll continue to increase the temperature of that steam. So what this plot is a calorimetry problem in disguise. Just like we did when we did the calorimetry problems by putting a piece of metal into a cup of water, we identified each of the Q pieces and we said there's one heat piece going into the metal or going out of the metal, and there's one heat piece for the water and the surroundings. We can do the same thing for this plot. Each of these different steps in the diagram is going to have its own Q piece, each of the different phases in red, and each of the different phase transitions in blue. So if we have a piece that looks like this, one of these like portions of the graph where you just have one phase, these are going to be the Q pieces that look the most familiar. Our MCAT equals Q, because the temperature is changing as we're adding in heat to this compound. If you have one of these pieces where you have a phase change that's happening, we are going to need the delta H value for that phase change. And we'll multiply that by N so that we can go from kilojoules per mole to kilojoules. All right, let's do an example using this graph that we already made. So let's say this graph is about ice converting to steam. So how much heat will be required to convert 135 grams of ice at -15 degrees Celsius to steam at 120 degrees Celsius. So if you didn't have a picture like this, I would recommend drawing a picture when you get a problem for calorimetry that involves more than one phase change. And so we want to first think about what are the important phase change temperatures here. So we know that the freezing point for water is at 0, and the boiling point for water is at 100. And we see that the temperature of the solid is below its freezing point, and that the temperature of the vapor is above its boiling point. So we're going to have a lot of different steps in this graph. So I like to think of it the same way I did in the last chapter, trying to find the Q total and adding up all the different pieces. So we're going to have one piece for each of the phases that are being warmed. So we're warming up that ice. We're warming up the liquid water. And we have to warm up steam. And we're going to have Q pieces for each of the two phase changes. So there's going to be Q for fusion and a Q for vaporization. So these three pieces are going to be like the red pieces. And those pieces are going to have Q equals MCAT. And for the phase change pieces, they're going to be like the blue pieces. We use delta H. So let's get this equation set up so you can see what it looks like. So for Q of ice, we have the mass of ice, the specific heat capacity of ice, and the change in temperature of ice. And keep in mind that the specific heat for solid ice is different than the specific heat for liquid ice. So let's write those here. So for solid ice, the specific heat is 2.09 joules per gram per degree Celsius. For liquid water, it's our favorite number, 4.184 joules per gram per degree Celsius. And for steam, gaseous water, it's going to be 1.84. The gas can't hold very much energy. Okay, so we're going to use the CSP for ice in this case, and when we do the temperature change, it's only going to be the temperature change that the ice experiences. So the ice's final temperature isn't going to be 120 degrees, it's going to be the point where solid ice turns into liquid ice. So that's going to be the 0 degrees as the final and the -15 as the initial. So there's going to be one of those, and there's going to be one of those for liquid water. So mass of liquid water, which should be the same as the solid water because none of it disappeared. The CSP for water, and the change in temperature for water. And water was never at -15, and it was never at 120. It was in between. It was in between the boiling point and the freezing point. We are going to have a piece for the steam. So the mass of the steam, which should be the same as the mass of the ice because none of it disappeared, the CSP of the steam, delta T of the steam, it finally ended up at 120 degrees minus the lowest temperature where we had steam is at the boiling point, which is 100 degrees. Those are our 3 phase pieces. And then for the phase change pieces, those are going to be number of moles of ice times the delta H of fusion, and the number of moles of water times the delta H of vaporization. So these can get a little long. They have a lot of terms in them, and I'm not going to deprive you of the privilege of solving it. I'll leave that for you to find the answer here. But you have one term to match each phase of your picture. So it's most helpful if you draw a picture for this problem so you can make sure you have all of the different Q pieces. And that is how we figure out how much energy it takes to change multiple phase changes from solid to liquid to gas and step all the way through. And the next video will be about how to read phase diagrams with temperature information about all of these phase changes.